So next I want to talk about the integral test. And the integral test is one where this is very useful. It turns out that you can tell whether or not a series converges or diverges based on the corresponding improper integral. And the idea of the integral test is very straightforward. So I just want to emphasize what that is, and then we'll succinctly write the integral test in a second. We're considering functions that go to 0 because we know by the divergence test that if the sequence does not tend to 0, then the series is going to diverge. So the only series that have a chance of converging are the ones that go to 0. Of course, not all the series that go to 0 are going to converge, for example, the harmonic series. But if the series does not converge to 0, then we're done. So let's assume that we have a series, or a function rather, that goes to 0, so something like this. And we have to kind of concern ourselves with how fast does it go to 0, and that'll tell us whether or not it converges or not, whether it converges or diverges. So let's say that we have just the value 1, and then the value 2, and we'll look at a few of these. Okay, not evenly spaced out because I can't draw. Okay. And so what I want to do is I want to think about the fact that this first rectangle, so let me actually finish drawing this rectangle here. Let's draw this all the way up and then connect that over. And we're going to do this with all the others. Okay. And connect that and then draw that all the way up. Okay, this is the idea. And what I want to do is I want to think about the area of these rectangles. Now this is going to have height f of 1 and width 1. So this rectangle is going to have area f of 1. Okay, so this is going to be f of 1 plus this area will be, again, width 1, height f of 2, and so on. And so if we add up all these values, now remember that instead of writing f of 1 and f of 2, we normally write that this is the sum a sub n as a goes from 1 to infinity. So the red area, the area of all the rectangles that sticks just above this function here, is going to be this series a sub n, where a sub n is, so let's say that this curve here, I need to make this a different color so we can see it a little easier. Let's make this curve maybe, I don't know, what do we want? Maybe let's make this black. Okay, maybe that makes it a little easier to see. And then, so this black curve, we're going to call f of x. And then a sub n is going to be just the values, just the points on that curve corresponding to 1, 2, 3, and so on. Okay, this could easily extend to 0 as well. We just didn't draw it. Right, so those points right there are the values f of 1, f of 2, f of 3, f of 4. In other words, the values a1, a2, a3, a4, and so on. Now, what we're saying here is that we have a function f where if we plug in a positive integer, what we're going to get is the value of the sequence at 1. Okay, so that's the relationship there. So f sub n is going to be, or the value of the sequence, I'm sorry, at n. So f of 1 is a1, f of 2 is a2, and so on. Okay, so that's the relationship between the sequence and the function. And you can, it turns out, relate, the integral test tells you that if one converges, then so does the other. In other words, if the series converges, then so does the improper integral, and vice versa. And so what I want to do is I want to think about taking this area here. Let's make this pink. So let's take this area here that's above the curve. Okay, so that area, that area, that area, and so on. And if you were to take all of these values and kind of take this purple piece here, and then you were to slide it over so that this purple piece was over here, and then you would slide this one over so that this piece is down here, and this piece is here, and that piece is there, and so on. What this tells you is that this value, a sub n, is going to be, well, it's equal to the improper integral. So the integral of f from 1 to infinity plus this pink stuff. this error terms. And you can really bound the error terms by just noticing that when you slide all of them over all the way to the leftmost rectangle, they all fit neatly inside that first rectangle, which we said is f of 1. Okay, so this tells you one thing that we need to know already, and that's that if you take this sum, a sub n, as n goes from 1 to infinity, that's going to be, let's see, that's going to be greater than or equal to the integral of f, okay, plus f of 1. Okay, so it's going to be the integral of f from 1 to infinity plus f of 1, okay, based on what we just said above. On the other hand, this sum, a sub n, is going to be, now maybe I have this inequality backwards. Sorry, yeah, this is going to be less than or equal to. I need to think about this here. Yeah, so I have this just slightly backwards. But the sum a sub n is going to be the areas of all the rectangles added up. That's going to be the same as the improper integral, so that's the red part, plus the pink part. And the pink part is less than or equal to f of 1. Okay, so we want that to be less than or equal to. On the other hand, a sub n, if we add it up from 1 to infinity, is greater than or equal to the integral from 1 to infinity. What I said before, by the way, was true. It's just not helpful. So anyway, so the sum here, the area of the rectangles, is greater than or equal to the area under the curve from 1 to infinity. Okay, so altogether what this tells us is that you can write this as one succinct inequality, and this is the integral test. Okay, so the integral test says that if f is a strictly, actually it doesn't even have to be strictly, if it's a monotone decreasing function, so if it's monotone decreasing, I've defined that for sequences but not functions, but it's the same idea, it's just that it's a non-increasing function, if you like. So if f is a monotone decreasing function, and if f of n is equal to a sub n for all integers, n, say, greater than or equal to 1. Okay, I'm just going to start this at 1, and then you can adjust this if this starts at 0. Just change all the 1s to 0s, of course. Then we have the following. So the integral from 1 to infinity of f is going to be less than or equal to the sum, a sub n, as n goes from 1 to infinity. And that's less than or equal to the integral from 1 to infinity plus f of 1. Okay, and so that's what's called the integral test. And the reason why this is relevant is that sometimes evaluating integrals is easier than evaluating sums. And so it turns out that if this number converges, so if this integral converges to, say, 5, and if f of 1 is 2, I'm just making up values, but if this is 5 and if this is 7, okay, so if this is 5 and if this is 7, then this series is going to converge because all the values, I forgot one important thing here. If f is a positive in monotone, so f has to be positive in monotone decreasing function. Otherwise, if it's monotone decreasing and if it dips below the x-axis, then everything diverges, and this is useless anyway. So this is really only helpful if it's positive and monotone decreasing. Anyways, but there we go. So if the series converges, so does the improper integral, and vice versa. If the improper integral diverges, so does the series. So whatever happens to one happens to the other. So if this goes to infinity, then you know that this sum in the middle is also going to go to infinity. There's no choice. It's kind of squeezed between those two infinities, so it also has to go to infinity. So this is the integral test. Now, I want to emphasize that this value, the integral from 1 to infinity, does not tell you what the series converges to. So a famously difficult example is what's called the Basel problem, named after Basel, Switzerland, or the Basal problem. And that is determining 1 over n squared. So it's known that this series converges, but for a long time, until the early 1700s, nobody had a proof that it converges to a particular number, and it happens to converge to pi squared over 6. One of the first things that made Euler a famous mathematician is that when he was in his early 20s, he solved this problem and showed rigorously that this series converges to pi squared over 6, or rigorously at the time. Okay, so he made a few jumps, but it turns out that they were justified. So the series converges to pi squared over 6, which is, if memory serves, something like 1.6 something. It doesn't really matter what it converges to, or it doesn't really matter what that number is. It's something like 1.5. On the other hand, so if you were to look at the integral from 1 to infinity of 1 over x squared, which would be the corresponding continuous function, this is 1. So you integrate, you get negative 1 over x from 1 to infinity. At infinity, it goes to 0. At 1, you get 1, and altogether, you get 1. Okay, so the point here is that both of these numbers are finite. The sum of 1 over n squared is going to be less than or equal to 2, and the reason why you know that is based on these bounds, right? You know that this integral from 1 to infinity is 1, and you know that f of 1, if the function is f of x equals 1 over x squared, that's also 1. So this side is a 2, this side is a 1, and since everything here is positive, since all the terms in the sequence are positive, and since it's bounded, this will converge by the monotone convergence there. Okay, so that's the integral test.